So we've talked about the binomial distribution a little bit, and now we're going to talk about binomial probabilities a little bit more in depth. The first part just asks us to determine which of these settings is/are binomial. And as far as the notation goes, if we have a binomial random variable, we can use the little squiggly line. So x follows a binomial distribution, and our two parameters are n and p. So n is the number of trials, and p is the probability of success. So the first one says flip a coin 10 times and let x be the number of heads. Well, that's absolutely a binomial case. The number of trials would be 10 for the 10 flips, and then the probability of success, assuming it's a fair coin, would be 0.5. The second one says roll a die 20 times and let x be the number of times a 4 was rolled. So that's still a binomial scenario. The number of trials would be 20, and then the probability of success, assuming this is a standard die, would be 1 out of 6. Number 3 says flip a coin and let x be the number of flips to get 4 heads. Okay, so that's our first case where this actually is not a binomial scenario. And if we think about the BINS conditions, B-I-N-S, those conditions, the one that it fails is the number of trials. We don't know how many trials, if we just start randomly flipping a coin, how many trials is it going to take for us to get 4 heads? So it fails that fixed number of trials condition. Okay, so number 3 was not binomial. Number 4 says draw 8 cards from a well-shuffled deck without replacement and let x be the number of red cards. So a success would be a red card, but this scenario actually is not binomial either. And the reason being is the key word here. If you're drawing those cards, those 8 cards, without replacement, that means you're changing that probability every time. So the trials are not independent of each other. The probability of success would be different for each draw. So had this said with replacement, then yeah, this would be a binomial scenario. But without replacement, you're taking the cards out, you're changing the deck every time. Okay, and then number 5 says a quality control engineer takes an SRS of 10 computer chips without replacement from a lot of 10,000 chips, of which 0.5% are flawed. Let x be the number of flawed chips in the sample, and the sample apparently is 10 computer chips. So yeah, this one again is without replacement, so x would not be a binomial random variable, but it would actually be really close. And the reason being that sample size of 10 computer chips isn't very many compared to the huge population size of 10,000 chips. So this one is actually really close to being truly binomial, and the reason being is because the sample size is so small compared to the population size. This goes back to the 10% condition. We'll talk more about that in a little bit. Number 6, the last one here, says IQ scores are normally distributed with mean 100 and standard deviation 12. Well, that's interesting. An SRS of 25 scores are drawn. Let x be the number of scores that are above 110. So this is actually a countable scenario. In fact, x would be binomial. A success would be getting an IQ score above 110. And apparently there's 25 trials, right? We're going to draw 25. Now, what's the probability of getting a score above 110? Well, you'd have to do some normal CDF calculations to figure that out. But a success in this case would be an IQ above 110, and then a failure would be an IQ of 110 or below. So if you could figure this out with a normal curve, normal CDF, you could tell me what the probability of a success would be. And that's actually pretty easy, but we're not going to do it right now. 6, binomial distribution. 25 scores at random. A success is the IQ score above 110, a failure, IQ score 110 or lower. So this one would be a binomial setting. Okay, let's go to example 1 here. It talks about a 12-item multiple choice test. It says it has choices A through E for each question. A student guesses on every question. Great job. So students giving a total random guess on each question. Let X be the number of correct answers out of 12 that the student gets. So for starters, this is a discrete random variable because we can count how many questions the kid gets right. And more specifically, we could say x is a binomial random variable. It follows a binomial distribution. The number of trials would be the number of questions on the test, which is 12. And then the probability of success, if you're just guessing, well, A through E, that's 5 choices. So there's a 1 out of 5 chance that you get the right answer. So that's the probability of success, 1/5. So what's the probability that x is less than or equal to 2? Or in other words, the probability that the kid that's randomly guessing on this test gets 2 or fewer problems right? Well, there's a few different cases we have to look at. The kid could get 0 right, the kid could get 1 right, or the kid could actually get 2 right. So if we add up these 3 probabilities, that represents the probability that the kid got 2 or fewer questions correct. And pretty simple, as long as we know to use binomial CDF, because x is a binomial random variable. The n would be 12 trials, p is 1/5 for a success, and then the x value we're interested in going up to would be 2. So that gives us our answer of 0.558. So a pretty good chance that the kid's going to get 2 or fewer questions correct just by randomly guessing on this test. Okay, the next one here says find the probability that x is greater than 4. So to get more than 4 questions correct, that means the kid either got 5, 6, 7, 8, all the way up to 12 questions correct. We could try to calculate each one of those individually, or we could use binomial CDF again. The only thing is, binomial CDF gives us the area below a certain boundary. So the easiest way to go about one where x is greater than a number, so all the stuff bigger than 4, like 5, 6, 7, and 8, let's just do 1 minus all the stuff 4 and below. So that's the big takeaway here. Let's make this easy on ourselves. Since the binomial CDF command only reads the lower area, right, the lower probabilities, and accumulates starting from 0, let's go up to 4 and then subtract that from 1. So if I use binomial CDF, n is 12, p is 1/5, and now my x value I'm going up to is 4. So now that I've got that, I have 1 minus, and in green here, this is what I got from the binomial CDF command. It's 0.9274 for a grand total of 0.0726. So pretty slim chance that the kid gets more than 4 questions correct. Okay, so now's where it starts to really get interesting. What's the probability that the kid gets between 2 and 6 questions correct? And we're including the case where the kid gets only 2 or the kid gets up to 6. Okay, so let's try to illustrate this for a moment in a table. So let's start with the x values on top. The kid could get 0, 1, 2, 3, 4, all the way up to 12 questions correct by guessing. And then the probabilities, we don't know each one of these individual probabilities, right? I mean, we could go through and find them all with the binomial PDF, the one that does individuals. But I just want to illustrate this for a moment. We just found the probability that the kid gets more than 4 questions correct. And we did that by subtracting, we did 1 minus all these, right? The probability that's less than or equal to 4. So we did 1 minus this pink part. And that left us with all the other cases. Kid gets 5 or 6 or 7, all the way up to 12. So we had to do that because the binomial CDF command only gives you the area for the lower ones. It accumulates up to a certain value. So in this case, we want to know the probability the kid goes between a 2 and a 6, and we're going to include 2 and 6 in this interval. So how can I focus on getting the values for just these? And I guess if you want to go through and do each one individually, be my guest. I'm going to show you a more efficient way. I just want from 2 to 6. I don't want the stuff above 6, and I certainly don't want the stuff below 2. What's the probability the kid gets between 2 and 6 questions correct? Okay, so let me erase that part for just a moment. So let's start with the upper bound here is 6. Can you just give me what's the probability that the kid gets 6 or fewer questions correct? Okay, so if I just focus on that, I'll make a gold box here. Okay, the kid gets from 0 up to 6 questions correct. I can easily do that in my calculator with the binomial CDF command. But then I really want to throw away these 2 cases, the 0 and the 1 case. So once I get this answer, this big gold box here, represents a bigger probability, I can subtract the probability that the kid gets 0 or 1 questions correct. So that I can put that in a blue box. I can subtract that part, and both of these I can get in the binomial CDF command. So we can start with binomial CDF up to 6, get that answer, minus the binomial CDF up to 1. And this is way more efficient than trying to type in binomial PDF for each one of these individual scenarios and then add those all up. So we start with just give me all the stuff less than 6, that's what binomial CDF does, and then subtract all the stuff that's 1 or lower. So in the gold box, that'd be 0.996, and then subtract the blue box, that'd be 0.275 for a grand total of 0.721. Okay, so I tried to illustrate that with a table. It's a really important skill for you to understand as far as how to calculate these intervals. Start with the upper bound from 0 up to 6, and then delete the lower bound, the stuff that you don't want. All right, so example 2 is about a roulette wheel. It says a roulette wheel consists of 38 slots. There's 18 black, 18 red, and 2 green. Let X equal the number of the next 10 spins of a roulette wheel that land on black. And here's my little roulette wheel for this example. And we'll just make it bigger for right now. So let's start with the mean and standard deviation of X. So if you spin the wheel 10 times, on average, how many times will it land on black? And what's the standard deviation of how many times it will land on black? So for starters, X is a binomial random variable. We know that. The number of trials in this case would be 10 trials. And then the probability of a success getting a black would be, well, there's 18 black slots out of 38 total slots. So P would be 18 over 38. And I'm just going to leave it that way. There's no need to simplify it or try to get a decimal at this point. So the probability of success is just 18 black slots out of a total of 38 slots on the roulette wheel. So the mean, and this is actually on the formula sheet, right? For a binomial random variable, you just do n times p. So 10 spins times the probability of success gives us 4.737 black slots. So how do we interpret that? Does that mean the next 10 spins I do, I'm going to get 4.737 black slots? No. That's the long-term simulation approach, right? So in 10 spins, we would expect an average of 4.737 black if we did this many times, right? If we repeated the 10 spins many times. So that's that simulation approach. Okay, now for the standard deviation. And this one's on the formula sheet as well. It's the square root of n times p times 1 minus p. Well, if 18 out of 38 is the probability of success, 1 minus p would be the probability of a failure. So all the other slots, which there's 20 left over, so 1 minus p would be 20 out of 38, which gives us 1.579 black for our standard deviation. And to interpret that, that means after we do the 10 spins, we'll typically be off by this much. Right? And I know this is a discrete random variable, so it's not going to, how am I getting a decimal? Well, that's if we do this many times, right? So we'll typically be off by 1.579 black from the mean, which we already did the mean, that was 4.737, if we repeated this many times. All right, I've got to make the wheel small again since we're doing the next part here. Part B says, how often will the number of spins that land on black be within 1 standard deviation of the mean? So I think this is actually a really interesting question and unique because this is a discrete or binomial, to be more specific, scenario. So let's start with the mean of X plus or minus 1 standard deviation, because it says within 1 standard deviation. That means it could be above or it could be below. So we have the values for the mean and the standard deviation. So we can start with the mean is 4.737 plus or minus 1.579, which was our standard deviation. So we're actually going to get an interval of values. Let me move my wheel a little bit more here. So if we take the mean plus 1 standard deviation, that's our upper bound. And if we take the mean minus 1 standard deviation, that's our lower bound, which leaves us with 6.316 for the upper bound and 3.158 for the lower bound. So really we're asking, what's the probability that x is on this interval? And how did we get the interval? We took the mean and we added the standard deviation. For the upper bound and the lower bound, we subtracted the standard deviation. What's the probability that x, which is the number of spins, is within one standard deviation of the mean? So what's the probability that x is between 6.316 and 3.158? And one thing I want to mention, this is the big emphasis, the big takeaway that's kind of unique about this problem. When we start talking about x being between these two decimal numbers, we need to keep in mind that x is a discrete random variable, meaning you can only get maybe 6 or 7 or 8, these whole numbers, as far as how many times the roulette wheel actually lands on black. So we can't get 0.3 or 0.158. So why do I mention that? We need to actually update this to something that's reasonable. To be within one standard deviation, let's think about a number line. So if I mark off where I think 3.158 would be versus where I think 6.316 would be, again, I can only use countable numbers. Those won't work. But I do see 3 countable numbers in between there, meaning I could use 4, 5, or 6. So that's really what this question's after then, because it's a discrete random variable. What's the probability x is less than or equal to 6, but greater than or equal to 4? So that's the major step in logic here. You notice that there's some decimal values here, but you remember x is a discrete random variable, so you need to think about on a number line which values this would actually include, which values this would actually take. And we show that here. And then this, you can actually use binomial CDF to get the answer. And we just talked about how to do an interval question with binomial CDF. You should get, and check me on this, you should get 0.649 as your answer. If you thought it was going to be 68%, you're close, but that won't quite get you credit. We need to actually calculate it here. And nobody ever said x was a normal random variable, so you shouldn't expect 68% to be the answer. Again, feel free to check me on this one, but you should be about 0.649 to 3 decimal places. Okay, so the last thing I want to feature in these notes is a little bit about the 10% condition and to prove that it works. So if we're sampling without replacement, which most of or almost all of the real-world sampling that's done, people don't use a true SRS, right? They sample without replacement. So the key fact is that if the population that we're sampling from is much larger than our sample size, and when I say much larger, I mean at least 10 times larger than our sample size, the trials will be virtually independent, and by that I mean to a few decimal places. The answers will be the same. So in some cases, when we meet that independence condition, we can say the distribution is approximately binomial. Right? So maybe the trials aren't truly independent of each other because we're sampling without replacement, but as long as the 10% condition works, we can say the distribution is approximately binomial. So the 10% condition, we've actually used this a ton already. We know we want the sample size to be less than or equal to 1/10 of the population size. Or if you prefer to not use fractions, you could just say 10 times n, right? 10 times the sample size is less than or equal to the population size. That says the same exact thing, right? One of these I just multiplied both sides by 10. Okay, so let's illustrate that the 10% condition actually works with a little NASCAR example here. It says a cereal company put one of 5 different cards inside each box of cereal that they produced. Each card featured a different NASCAR driver: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. Suppose that the company printed 20,000 of each card, so there were 100,000 total boxes of cereal with a card inside, right? There's 20,000 of each card, and there's 5 drivers, so that makes up 100,000 boxes of cereal with a card. If a person bought 6 boxes at random, what's the probability of getting no Danica Patrick cards? That'd be really sad. Okay, so what I want to point out to start is that we're sampling these cereal boxes without replacement, right? The person wants to take these 6 boxes home, eat the cereal, and get the cards. They're not replacing the boxes, so they don't have a chance to be selected twice. So these trials would not truly be independent because we're sampling without replacement. But if you compare the sample size, 6 boxes of cereal, to the population size of 100,000 boxes of cereal, you'll notice that 6 is way below 10% of the population. 10% of the population would be 10,000. So never fear. I know it's not truly independent, but the 10% condition works for this case. So we can say since the 10% condition is met, the distribution is approximately binomial. In other words, they're pretty close to being truly independent, even though they're not quite. And we're going to see just how close they come here. So the distribution, we'll call it approximately binomial. The parameters, n and p, right, we know n is 6. The probability of success, well, if you can randomly get 1 of 5 drivers, right, p would be 1/5. So Danica's on 1 of 5 cards. So using this binomial logic, right, and I'm going to use the binomial formula here, the probability that we get 0 Danica cards from those 6 randomly selected boxes, well, that would be 6 choose 0, and again, I'm going to use the formula from the formula sheet just so you're used to the notation. 6 boxes of cereal, choose 0 winners, times 1/5, that's the probability of success, to the power of 0, so 0 successes. 4/5 would be the probability of a failure in this case, and that's to the power of 6 because the 6 boxes would all be failures. No, that's the notation from the formula sheet, right? If you want to do it in your calculator, you would just say binomial PDF, n is 6, p is 1/5, the x value would be 0. And again, I just want to acclimate you to the notation that you might see on like a multiple choice question. If you're on a free response question, you can always use binomial PDF or binomial CDF. The answer is 0.262144, and it's actually important that I take it out to that many decimal places here. And the reason being, we said that this wasn't truly independent, right? Because they didn't sample those 6 boxes of cereal without replacement. So what if we looked at not making this a binomial case? What's the true probability? Right? What's the actual probability of getting no Danica Patrick cards from 6 randomly selected boxes without using that binomial approximation? In other words, without assuming that they got replaced somehow. So let's say we had 100,000 boxes of cereal to choose from. We're going to randomly choose 6 boxes. And we are still going to take the box and keep it, right? We want the card in the cereal. So let's start with the first box. If there's 20,000 of the Danica cards floating around out of the 100,000 boxes, then the probability we don't get one in the first box would be 80,000, because there's 80,000 losers in this case, non-Danica cards, out of 100,000. That's our first box. And then our second box, we ate that box of cereal. Our second box, there's 99,999 left with 79,999 losing cards left. So hopefully you catch my drift. There's 1 less total boxes and there's 1 less boxes without a Danica card in it. And then we get a little bit lazy. That's okay. First box, second box, eat a few more boxes all the way down to the 6th box where we have 99,995 boxes of cereal left to choose from and 79,995 non-Danica cards left. So this would be the true probability. This would be the true probability without using the approximation for the binomial, which gives us, and you can check this in your calculator, right? Multiply these 6 fractions together. 0.262134. Wow. So let's make the comparison here. Those are actually very close. In fact, they're the same down to 4 decimal places. They're the same down to 4 decimal places. So the 10% condition actually works really well, especially when that population size is so much larger than our sample size. So example 4 goes back to a hiring discrimination simulation that we ran first semester. It says, an airline has just finished training 25 first officers, 15 male and 10 female, to become captains. Unfortunately, only 8 captain positions are available right now. Airline managers decide to use a lottery to determine which pilots will fill the available positions. So I guess that's an interesting way to pass out the jobs, right? Of the 8 captains chosen, 5, I should say female, 5 are actually female, and only 3 are male. So this scenario actually happened to one of the author's sons, and some of the males, for some reason, thought the lottery was off or thought they were being discriminated against, right? Hence the name of the question. Little did they know that one of the guy's dads was a stats professional, so he could prove it right away, whether it was or not. So the first part says, explain why the probability that 5 female pilots are chosen in a fair lottery is not this binomial scenario. So it looks like they're using X to represent the number of females chosen, right? X is a random variable, the number of female pilots chosen. And this is to be a captain. So they have 8 captains positions that they're going to use for the lottery. So there's 8 total captains, so it's 8 choose 5. So the 5 represents the 5 female successes in this case. And then 0.4 to the 5 means 10 out of the total 25 officer candidates were female. So that'd be 40% female successes for 5. So the 0.4 to the 5, that's the probability of getting the 5 female captains. And then 0.6 to the power of 3, well, that's because 15 out of the 25, or 60%, were male candidates. So that would be the 3 male captains. So the actual is this not representing the scenario correctly? And the reason being is X doesn't follow a binomial distribution. Why is that? Which condition does it fail? Well, it's sampling without replacement each time. So we can say it doesn't follow a binomial distribution because we're sampling without replacement when we're choosing captains, right? You can't be chosen as a captain twice. Okay, well, how about the 10% condition? Would that work in this case? And actually, no, the 10% condition doesn't even come close. So we can't say that this thing is even approximately binomial. So this thing is not valid. The 10% condition isn't even close because if we're sampling 8 people, right, 8 trials in our lottery, so we're sampling 8 pilots out of a total of, there's 15 male and 10 female, so a total of 25 pilots, that means we're sampling 32% of the total population of pilots in this case. So the 10% condition is not even close. We're sampling way too many for this to be credible. You know, if we were just selecting 2 pilots, well, that would be less than, 10% of 25. But since we're selecting 8 pilots to be captains, we're selecting 32% of the population. That's way over the 10% condition, so that doesn't work here. So this 0.124 answer would be incorrect for sure. Okay, so then what is the correct answer? It says calculate the probability that 5 or more females are chosen, and this is what we previously approximated with our simulation. We got a p-value and everything. So the probability that X is greater than or equal to 5. So 5 females or 6 females or 7 females, or heck, maybe the lottery picks all 8 females. And I wouldn't expect you maybe to know this right away off the top of your head. In fact, you won't even have to use this notation, but it's nice to illustrate it here. We did this in the last notes. I wanted to use N choose K. So we're going to have a lot of pilots to choose from, and I want to use the math behind that. So how many different options are there to choose K pilots? And if you want to follow me with this, the calculator commands would be math, and then go to PRB, and then it's NCR. So for starters, let's say we get 5 females. Well, the total number of selections we could make, we have 25 candidates between the males and the females, and we're going to choose 8 pilots. So if I do 25 choose 8, that tells me the total number of ways that I could choose 8 pilots from that group. It's a big number fraction here. And then for the top of our fraction, what's the probability that we select 5 females, and then the other 3 would have to be males? So we have 10 females to choose from, so we could say 10, and we're going to choose 5 of those to be captains. So 10 choose 5 times, well, we have 15 males to choose from, and then the other 3 captains have to come from that group, so 15 and then choose 3. So that represents the case where we have 5 female captains. What about the case where we have 6 female captains? Well, the denominator would be the same, right? We have 25 people to choose from, and we're going to choose 8 captains. And then for the females, now we have 10 choose 6, and then we have 2 positions left for the males, so it would be 15 choose 2. And then the case when there's 7 female captains, we would have the same value in the denominator, 25 choose 8, total possible outcomes. And then we have 10 females, we're going to choose 7 of them. And then 15 males, we're only going to choose 1 male for this group to get our 8 pilots. And then lastly, to get all 8 females and no males as captains. So we still have 25 choose 8 on the bottom, and then 10 females, we're going to choose 8 of them to be captains, and then out of the 15 males, we choose 0. So that's the case where you would have all 8 females as captains. Okay, so for each one of these fractions, the number on the bottom is going to be the same. How many different groups of 8 can we pick from those 25 pilots? And I told you it's a pretty big number, 1081575. So that's 1,081,575. So that's at the bottom of our fraction for each one of these. And that represents all the different combinations of 8 people, of 8 pilots, that we could choose out of that group of 25 pilots. Okay, and then the numerators, you'll notice they get smaller. Each scenario is less and less likely. So to have 5 female captains, there's our numerator. To have 6 female captains is a little less. The chance of getting 7 in the lottery, a little less. And the chance of getting 8 females and no males in the lottery, only 45 out of this big number. For a grand total of 138,555 different ways over our denominator, which is approximately 0.128, which is a different answer than the scenario before. I think it was 0.124 that was before, so that was incorrect. The true answer would be 0.128. The funny thing is, I know some of my classes actually got really close to that when they did a simulation, and their p-value was how many of the dots were 5 or above, and they got really close to about 12 or 13%. Okay, the great news is you won't be expected to actually use this scenario, this formula, on the AP exam or on our exams, but it was nice to illustrate it here. So we talked about the 10% condition, and we talked about calculating binomial probabilities again. That's all for these notes. I'll see you in class.